we have chosen our young researchers that will present them. So it means they have to be at least PhD students or postdocs, but they cannot be senior researchers like tenure track or tenure researchers. Okay, so please, Marcela, go ahead.
Now we will move to the presentations of young researchers. So we will start with the first award package. Lukáš, Zezula, mine. So please, the floor is yours.
Sure. Now you can see me. So good afternoon. I would like to introduce to you my research in fault diagnostics of electric drives. So the primary objective of my research lies in realizing fail operational drives for electric motors. For this purpose, we are utilizing the model-based principles. So basically, we formulate some mathematical description of particular fault and transfer the continuous time model into the discrete time domain. And we are using the discrete time models to track the healthy motor behavior. For example, we are monitoring some electrical parameters like resistance and inductance, and we are also utilizing the discrete time models for fault detection, thus tracking the time moment when the fault occurs. And after the fault is detected, we are using some fault feature extraction algorithms, which enables us to track, for example, fault location and fault severity. And we plan to utilize these estimated informations in optimized fault mitigation and update control actions into the faulted motor to obtain healthy-like behavior in costs of the motor performance. The research approaches that we are relying on are mostly based on Bayesian inference, and we are utilizing the Bayesian inference for parameter estimation, model comparison, but also for decision making to detect the fault occurrence. And for the achieved results, we designed the model-based diagnostic algorithm that is computationally efficient and enable fault features extraction even during the transient state, which was a challenge because most of the currently utilized algorithms rely on some steady state observation, and we formulate model-based approach that functions even in the transient state. You can actually see some of the results in the bottom right picture, where we estimating, for example, probability that phase A is shorted, that's the third row, and we estimating the fault severity, that's the proportion of the winding shorted by the zero resistance. And we are estimating in steady state, load transient, and velocity transient. And for the future research, we plan to improve the model by, for example, incorporating some higher harmonics of permanent magnet fluxes and so on. And we plan to design model predictive control based fault mitigation methods to optimize the control actions. Thank you for your attention.
Thank you very much. Next speaker is Adrian Saldanha.
Hello, everyone, and welcome to my short presentation. So, my research is into the design of algorithms for non-collocated vibration absorption. And what we mean by that is basically that the actuator is not directly attached to the target at which the vibrations are to be suppressed. And additionally, in this research, we also take into account we also expand our current methodology to include multi-frequency absorption. And how we achieve that is by using delays in our control design. So we we take into account minimum state information, and we feed that into a delay-based controller. And additionally, we also use a dynamic controller, which further complicates our design. But because we have the tools available, and we systematically design our system, we are able to compensate for at least 4 frequencies as a benchmark case. And so far, we've achieved a proof of concept of this design. And despite that, we still have a few additional challenges. So the first is to account for system neutrality, which is when we use acceleration feedback. And the second is to improve the robustness of our controller. And yes, another thing to mention is that we collaborate with KU Leuven, with my professor Wim Michels, as part of this project. And lastly, just to showcase some of the what we mean by this. So basically, we have an absorber located at U1 over here, and we wish to silence vibrations at the mass M1. So we tune the control action using delayed feedback from the masses M2 and MA to target the vibrations at this mass. And the external disturbance that we consider are from this disturbance, which is from a voice coil. And these are the results that we have obtained till now. So F denotes the external disturbance, and X1, it denotes the oscillations at the target. Okay, so that's it for me, and thank you very much.
Thank you very much, Adrian. Professor Walter, you have a question, I suppose, related to the first presentation.
Okay, questions? Yeah, I wait.
Questions will be at the end, if it's okay for you. Okay, so we can move to the other, the third presentation, Yiri Zemanek.
Okay, good afternoon, everyone. I'm excited to share our recent work on feedback control for lattice structures, specifically focusing on physical model we call the voxel tower. Our work is motivated by concept of digital or modular materials, where structures such as this one are built from discrete building blocks. Previous research on these materials showed that they are excellent for creating lightweight and reconfigurable structures, but they often lacked feedback control. This means they couldn't respond to changes in real time. We aim to solve this by introducing feedback control for improved dynamic behavior. Next slide, please. In this video, you can see an example of active damping. So you can compare the behavior with active damping on and off. And here are the main innovations in our work. So first, actuated voxels. These are building blocks capable of local movement, allowing us to control the shape and behavior of the entire structure. Then second, data-driven control. We use a method called dynamic mode decomposition, which helps us build a model of the system using only data, so we don't need prior knowledge of the structure's dynamics. Third, control methods. We implemented 2 control strategies, linear quadratic regulator for stabilizing the system, and then Koopman model predictive control for tracking set path or desired path. Next slide, please. In this image, you can see comparison of the system with and without active damping. So far, we have demonstrated that the voxel tower can remain stable with very few sensors and actuators, even when external forces are applied. and it can accurately follow a set path, which is significant improvement over older systems that lacked feedback, showing that digital materials can be used in dynamic responsive systems. Next, we plan to apply our method to larger and more complex structures, testing how well we can control bigger systems while keeping them resource efficient. And I should mention that this work is in collaboration with the Center for Bits and Atoms at MIT, and we are exploring further real-world applications. So thank you for your time.
Thank you very much, Jiri. The next presentation is Slavek Zbirovsky.
Good afternoon, everyone. I will present next research project, and this project is focused on automatic conversion of point clouds into building information models. First, let me start with what are actually building information models. These models serve as a digital repository, and inside this repository we have a building, and each object is represented with its geometrical entity, and we can assign the properties to each element. These models are useful in different parts of a building lifecycle. We can use them in a construction phase. Also, we can use them in a phase at the end of the lifecycle, and they help us evaluate the process and maintain the building. Some older buildings doesn't have these models, so we are trying to recreate them with laser scanning techniques. And we are doing it nowadays manually, but we have developed a pipeline that can automate this process and save the time. We have combined the density-based analysis method with the computer vision techniques and morphological operations. Some of them you can see on the right. There is two-dimensional histograms, morphological operation on the mask, contour detection, edge smoothing, and there are many more operations. But in these, we will find that there are many challenges how to avoid some noise inside these elements. We have achieved some results. We have tested on 3 different data sets. 2 were from real world. One was a benchmark from University of Zurich. There are results on the top. On the right, there is a point cloud with the deviations, and on the left is the resulting model we have saved into IFC file format. We were able to identify various structures such as slabs, walls, openings, such as doors and windows. In future, we would like to extend the capabilities of our software to include many more objects such as beams, staircases, and roofs, and also implement machine learning techniques to find, for example, furniture inside the buildings. That's all from me, and thank you for your attention.
Thank you very much. Next presenter, Dwivedi, please.
So good afternoon, everyone, and I'm happy to present some of our key achievements in our research activity. And our primary objective was to bridge the atomic scale and micro scale to understand the material's property well, which we can use in anywhere, mainly with the extreme cases. And we use molecular machine learning for that. One of the key example which I took here for my research is nuclear fusion reactor, where you can imagine the material which actually withstand the plasma, which has extremely high heat load coming from plasma. It's mainly chosen tungsten because of its high melting point. But even though it's high melting point, because of extreme high heat load, as I said, it actually gets melted, which results in producing the dust particles, which you see here, from nanoscale to microscale. And these dust particles get the velocity and they impact back to the wall with extremely high impacts on the wall, which actually results in the crater, what you see here, which results in erosion of the wall and initiation of a crack, by which means that your structure is getting to be failure. So we try to actually understand this cratering phenomena by using atomistic scale modeling. And for that, the key ingredient is force field. So we try to optimize our present tungsten force field through machine learning to better capture the thermal properties. And then we achieve the cratering phenomena, which you can see here in detail. And we validated our cratering phenomena with experiments. So our present cratering scenario is well capture all the things which is going on there during the case of impact with experiments. And not only that, addition to it, you can also see the real time inside the materials that how these defects actually evolve. So you see that the defect actually, this line, what you see here is actually a line defect of a material, which is called dislocations. So these evolution of a defect directly implement the material properties. So now you can understand this, that how the material get degraded, and you can work on how you can enhance the property of a material. So this is the present research what we got, and we are trying to actually in the next step to put more ingredient on it and more variables where you can push our model to the main realistic things, realistic scenarios, which means that material should be polycrystalline, which is normal, and also in these cases like here in the nuclear reactor, you should there should also be neutron irradiation and these voids. So we are actually trying to implement all these things in our model to achieve more realistic phenomena and to understand the material degradation property well. Thank you so much.
Thank you very much. Now we move to the second work package, and Jan Behrens is the first speaker.
Hello, my name is Jan Behrens, and I'm presenting today the paper COBOS, Constraint-Based Online Scheduler for Human-Robot Collaboration. What we do here is online optimization of human-robot collaboration, where we have shared tasks and subtask dependencies. You see here on the right that the human and the robot have a shared tasks of building this block pyramid, for example, and each actor, back please. Yes. Each actor has access to certain parts of the assembly, and it's important that the dependency graph which you see on the left is not violated, so the tasks have to be executed in a certain order, and also the human and the robot may not collide. Oh. Next, please. Okay, so COBOS, our system is based on constraint programming. So it takes in the structure to be built, which you see on the top right, the observation from the environment, and the list of agents, and it encodes this as constraints or constraint satisfaction problems and calculates a solution. Then it requests from the actors, here the robot on the left via behavior tree, the action, or from the user via a graphical user interface. So why do we care about online planning? The reason is that we have in the human-robot collaboration high amount takes now, and also the human can reject certain tasks. So we need to close the loop, and that gives us the chance to balance the loads and reschedule the rejected tasks. Next, please. Okay, here you see on top the initial schedule, how the system schedules with the initial assumptions, and on the bottom the top two rows in the Gantt charts are for the human, the bottom two rows are for the robot tasks, and in the bottom Gantt chart you see how the Gantt chart evolves over time with more and more observations, and of course it gets longer. On the right you see a dependency graph which shows basically the live observations of which tasks are currently available and which tasks are already done and which are not yet available. Okay, next. The reactive robot control using behavior trees and impedance control allows that the robot is reacting online to disturbances, for example here the motion of the platform, or when the human enters the workspace, so that the tasks can be fulfilled efficiently and safely. Next, please. So we executed 56,000 simulation experiments where we sampled from distributions for all uncontrollable variables. And we found that our scheduling approach, our online scheduling approach, outperforms the other baseline methods and methods from the literature, and exhibits a lower make span in average and also a lower variance. Thank you for your attention.
Thank you very much. Next presenter is Matej Novosad.
Hello, I'm here to present our recent advancements in trajectory generations for agile UAVs. For who don't know, UAVs are unmanned aerial vehicles. You might know them under the name drones. Our group specifically focuses mostly in multirotors, which are robots mostly renowned for their agile capabilities. This means they're able to fly at very high speeds, while also being able to change their direction of flight almost instantaneously. Therefore, they're able to react to changes in the environment or new inputs from the computer almost immediately, or at least this is what theory would allow them. However, the state-of-the-art methods so far were divided in two different groups. One focused more on this real-time keyword, which you can see in the title of our paper, which means they were able to be computed in very short amounts of time online on the UAV. However, these models methods that use those models were basically not able to fully exploit the agile capabilities of the UAVs. The other side, on the other hand, focused more on the agile part, but completely disregarded the real-time part. These methods generated very agile trajectories, but took almost hours to compute or multiple hours to compute, which made them basically unusable online. So we came up with a method that is able to capture both real-time computation and agile flight. We do this by using a so-called point mass model, which focuses only on the translational dynamics of the UAV, disregarding the rotational ones. And those rotational constraints are employed just later with a controller, as you can see in the videos. The trajectories can be followed pretty closely. So our output is basically a trajectory generator that can be used online. It only takes a couple milliseconds to compute a very long trajectory. And this trajectory, as shown in the videos, can be followed with tracking errors that are comparable to the method that takes hours to compute. The trajectories in the videos that we present in our experiments were flown at 3.5 G acceleration and almost 100 kilometers an hour flight. So this proves that our method is capable of real-time computation of agile trajectories. Thank you very much.
Thank you very much. Next speaker is Shubhan Patni.
Hello, I'm here to present our work on tactile sensing in robotics. Tactile sensing is an under-experimented with technology in robotics. Computer vision is very good at object classification and object recognition, but there are some object properties that you cannot estimate just from vision. For example, the weight of objects, the stiffness of objects, the surface texture, smoothness, friction of objects, and all of these properties are still important to feed into robots for better grasping and better manipulation of these objects. So what we want to do is we want to evaluate how effectively robots and robotic grippers can estimate different physical properties of objects and then apply them. So we started with our robots. We have two anthropomorphic hands with a lot of tactile sensors, and we have two robotic grippers which have only current feedback. We made all of these different robotic grippers interact with our foams data set. As you can see, all of these foams look similar, so it will be difficult to separate them just using computer vision. But we collect a large data set with over 24,000 measurements, and we apply a lot of different methods, statistical methods, stochastic methods, even learning, and we achieve good classification accuracy on this foam set. Then the next step to do is to put this in an industrial scenario. For that, we make a second object set. This object set is made up of objects in 4 different categories: paper, metal, plastic, and wooden. and then we try to use our classifiers to classify these objects into their respective material categories. As you can see in the videos, the robot will now online in real time explore and interact with these objects and separate them based on their material characteristics. Thank you.
Thank you very much. Next speaker is Zdeněk, please.
Hello, I'm going to present our research focused on visual teach and repeat navigation. It's a framework which allows the mobile robot to autonomously traverse previously mapped paths. During the deployment, you typically build a topological map of the environment where the edges are autonomously traversable paths and the nodes are places crucial for the deployment scenario. One of the major issues for camera-based navigation currently is that every environment has some type of dynamics unless it's completely controlled. And with the time, your map gets outdated and it can cause the deterioration of navigation quality. So there are basically these three major concepts which are used to mitigate this issue. First of all, you can create a visual model which outputs a representation robust to the changes in environment. This approach is very handy in scenarios where you can anticipate the environmental changes, such as seasonal changes or day and night, which can be very prominent in the image space, as you can see in the bottom image. Further, there are some changes in the environment which cannot really be anticipated. So, for example, structural changes, some objects can move in the environment. And for that, we employ a continual learning. And this allows us to use data collected during the deployment and update our maps and update our models and keep the navigation quality good. And finally, some parts of the environment can have different, the dynamics can be faster, some parts can have slower dynamics. So the places which have the faster dynamics, you would like to visit them more frequently so that you can really build a good model of your environment. And in our latest work, in our latest paper, we present a type of visual teach and repeat navigation, which can easily incorporate all of these three concepts to prolong the autonomous navigation and ultimately improve the navigation quality. Thank you for attention.
Thank you very much. Next speaker is Grus, please.
So hello, I would like to talk about automation of placement for analog and mixed signal integrated circuits. Placement process is a phase of overall circuit design where designers determine where each different device, such as resistor or transistor, will be placed on the chip. Our work was initiated by ST Microelectronics company because, unlike in the case of digital integrated circuits, where the placement is already automated, it remains time-consuming and manual process for analog integrated circuits, and actually is quite a bottleneck for designers, so they want to automate it. We started with formulating our problem as an extension of rectangular packing problem, where we are given a set of rectangular devices and topological structures we need to place to create a feasible placement, which minimizes both the placement area and approximate connectivity between devices, so the subsequent step of routing is made as simple as possible. We also need to consider different constraints during our optimization. Namely, for example, there are different minimum allowed distances between devices depending on the fact whether the devices have different voltage levels, then we need to take them further from each other. Or in some cases, when conditions are met, we can actually merge the so-called pockets around the devices to make a more compact design, which can be seen here in the top figure. Another constraint is, for example, symmetry groups, where a group of devices needs to have the same axis of symmetry. This can be also seen in the figure here in the right part of it. How we solve this problem? We started with using integer linear programming. Work started by graph drawing, which we further improved with use of map heuristic, and then we developed a constructive heuristic, which was guided by meta heuristics, that is genetic algorithm, to provide a heuristic solution. We first evaluated our methods on synthetically generated and benchmark instances with hundreds of rectangles. Just for your information, the typical industrial example has less rectangles than it, so this was quite a nice benchmark. And after its initial experimentation, which can be, for example, seen in the bottom figure, we evaluated our methods on real-life instances provided by the industry partner. In 12 out of 17 instances, we are able to find a solution which was overall better than the accompanied manual design in both the area and the connectivity. In the rest of the cases, we are able to find non-dominated solutions, and we were able to find these solutions in just minutes instead of hours needed in the case the manual work was done. So this greatly highlights the potential of our work to improve the results. And at the moment, ST Microelectronics company is working for our solution for already 6 months, and we hope for the cooperation will bring more results regarding this problem of analog placement. So this is all from me. Thank you for your attention.
Thank you very much. Next speaker, Michal, please.
Good afternoon. I'd like to introduce our research on multi-agent pathfinding. So where we take the problem of scheduling movement of group of robots in an environment and we model it as a graph theoretic problem, where we discretize the environment as a graph where the vertices correspond to the places and edges to the connections. And we're given a set of robots. You can see it on the example here on the right. And for each robot, we have a starting and target position and some make span that we aim for. And we're trying to compute whether there is a non-colliding schedule of all the robots, such that each robot arrives at its target within the given make span. And the schedule is non-colliding, meaning that no two robots occur at the same place at the same time, nor they cross the same edge in opposite directions. And this problem is known to be hard in general. In fact, it's known to be hard even to approximate. So in general, we must resort to using heuristics or very inefficient time-consuming algorithms. So in our research, we focus on the complexity of the problem if the environment is somehow restricted, if the topology of the underlying graph or some other parameter of the instance is restricted. And in fact, we show that in several such cases, we are able to design efficient algorithms. So for instance, when the topology is similar to being a tree and we're looking for a solution of short make span, then we can solve this efficiently. Similarly, when even for arbitrary topology, but there are only a few agents and the make span is short, and we can also solve this efficiently. And moreover, we provide several matching lower bounds, showing that in some cases, we really can't hope for more than heuristics. For example, it's already hard if we restrict the topology to be a tree or on planar graphs with just make span 3. In the future, we also aim to first understand this sort of fine-grained interplay between the complexity of the problem and the structure of the topology. And also we are looking at other added constraints, such as that the agents should keep at all times within certain distance to be able to communicate with each other. Thank you.
Perfect. Thank you very much. And Hula is the last speaker.
Okay, hello everyone. So in this work, we look at the question whether neural networks can reason. This is a very hot topic. Everybody is discussing whether models like ChatGPT are already reasoning. Some people say yes, some people say no, they just memorize stuff. And everybody is an expert on that. But I think the problem is that we don't know what we are talking about, because reasoning is not well defined. It doesn't mean, we don't know what does it mean. So in this work, we focus more closely at the question whether neural networks can predict satisfiability of Boolean formulas. And if so, if it's possible, what's the mechanism, how they are able to do it? And the question whether it's possible, this was already answered before us by Daniel Selsam, who showed that you can train a graph neural network which operates on a bipartite graph of the formula, of the logical formula, where on one side you have constraints, on the other side you have variables. and you do message passing between these nodes, and you update the vector embeddings of the variables. And at the end, you take these embeddings and you apply some classification head to predict whether the formula is satisfiable or not. But there was no indication what's the process, like why does it work? So in this work, we explain or we show empirical evidence that what the neural network learned to do is it learned to act as a gradient descent solver for the semi-definite programming relaxation of MaxSat, where MaxSat is the optimization version of SAT, where you try to satisfy as many clauses as possible. And you can design approximation algorithm because the problem is NP complete still. So you can design approximation algorithm. And one way to do it is using semi-definite programming, where instead of optimizing over the binary values, Boolean values, you lift the variables to vector space and you optimize vectors. And then you round it back to the discrete case. And so we show that what the GNN of the graph neural network is doing, it's basically each update of the GNN acts as a gradient update on the SDP objective for MaxSat. And using this insight, we designed this curriculum training procedure, which allows us to train the modeling 20 times faster than the original thing. So now we have some idea why is it possible that these neural networks can do reasoning, because they can basically implement some algorithm which we understand. And yeah, okay, that's all from me.